Okay, I think we can get started. We'll see if some more people roll in a little bit later. A few announcements before we get into today's lecture and topics. One, from what I could tell with office hours and questions on problem set 2, you guys are done with it. I can see that it was one of the harder problem sets, and I'll respond to that accordingly with, I think, both the grading and of that problem set and the next problem set 3. If you find it reassuring at all, problem set 3 covers less lectures and also areas that I'm not as involved in with my research. I may have underestimated the time for some of the fluorescence questions since that's my area of study. So hopefully problem set 3 won't be as intense for you guys. That's one thing. The other thing is a reminder for next class will be the discussion about the light microscopy core. The current sign up sheet, it looks like it's about half the people have signed up already. So if you haven't signed up, go to that Google Drive sheet under the modules and please sign up for the groups. And then I'm thinking for the location for the groups that want to meet in person, since the last time it was a little bit loud, an alternative site that we're going to meet this time is going to be, I think it looks like it should be in a quieter area. It's a green space that's by, in between like the Art Museum and Tink. There's a white tent there with a bunch of picnic tables and we'll meet there. So I'll put that under the announcements and on Monday or Tuesday as a reminder to the groups that are signing up in person. And also then we can get a better assessment of like what the weather will be as well. So are there any questions about that?
Weren't those tents, I thought those were for COVID testing, but did they move that?
No, so I'll try to take a picture on my way home from campus today. It's not like enclosed tents, it's like a very large, I guess it's more of like a pavilion type area. So it's in that green space next to the MBA building in between the Art Museum. So I'll try to take a picture or do like a pin drop on Google Maps or something like that, if that helps.
Okay, yeah, I think I know what you're talking about now.
Yeah. And then I also posted some more details and a sign-up sheet for the semester end project. So you guys can pick a topic so we don't have people all presenting on like the same or picking the same instrument to write about. So when you have time, take a look at that, and whenever you've narrowed down what type of, this year-end project is supposed to be for you guys to get more in depth about a certain technique or even analysis method and some of the applications. So it's really up to you of what your interests are. And once you have something selected or maybe multiple ideas, if you'd like to talk to me about it, please set up a meeting. You don't have to wait for the class on October 15th to talk to me. If you want to discuss it earlier, you can. So any questions, comments? Okay. Let me share my screen. Yeah, so this lecture and then I guess the next lecture a week from now are going to get into looking at spin, both nuclear magnetic resonance spectroscopy, and then also electron paramagnetic resonance spectroscopy. We'll discuss both of those. Today we're going to be focusing more on the physics behind it, the phenomenon, and then the next lecture we'll get into more of the instrumental components and the application to biophysics and the like. Yeah, the goals today, we're going to be working, this again falls in the category where it's not all light-based. This involves both electromagnetic radiation and magnetism. The electric fields are going to be coming from the radio frequency range for NMR and the microwave range for EPR. And then this is all done in a magnetic field. So that's going to be orienting the spins of either the nuclei for, obviously with nuclear magnetic resonance, and electrons for EPR. So today we're going to be describing the physics behind it, both from a quantum perspective and a classical perspective. If you use classical physics versus quantum physics, you'll end up with the same equations to then quantify your NMR signal. And specifically, we're going to discuss some of the numbers or values that you get out are the relaxation times and also the chemical shifts. So what physical phenomenon are leading to these two things? So with our instrument schematic here, we're going to get into this more in a week from now, but your source includes both the magnets and your radio waves, frequency radiation. The sample is going to be your biomolecules or your cellular sample, but it has to have nuclei with an odd number or odd weight, and we'll get into that. Or if you're doing EPR, you have to have a free unpaired electron. Then we'll get into the detectors that are used for radio frequency radiation. And finally, we'll get into this more next week. There's also post-processing with our favorite Fourier transform, because many NMR instruments are going to be pulsed, and you have a free induction decay of your signal. For FID. So with this overview, these terms like the FID or these details, we'll get into the details of this throughout the lectures to give you guys some orientation. So NMR spectroscopy, the overall, how it works is you're going to have absorption of radio frequency radiation by nuclei in a magnetic field. Which I'll usually be abbreviating with like B with the vector notation there. So do you guys remember what range, either wavelengths or frequencies, the radio wave region of the electromagnetic spectrum is? So Sean's saying a millimeter. It's a little larger for what we're using here. Any other comments or guesses? Yeah. Todd's got, yeah. Catherine's saying on the order of meters, Todd greater than 0.3 meters. So our frequency ranges, if it's greater than, if we're in the meter range, the frequencies are typically less than 10 to the 9th hertz. So you'll hear about different NMRs and what frequencies are typically classified like as like a 400 megahertz or 100 megahertz setups or so. Is how they indicate the strength of, or the frequency range that the NMR works in. So a bit of background and history with NMR. It actually goes back to Wolfgang Pauli proposed the idea in 1924. So he was saying that he proposed that nuclei have spin, and that these can have the energy levels of those spins can be split in a magnetic field. So if you think back to your Gen Chem, Pauli was also the one who proposed electron spin as well, Pauli's exclusion principle. So it makes sense that he also was thinking about spin in nuclei as well. So that was way back in 1924, but it took until 1946 for the experiment. So that was done pretty much simultaneously by two different scientists, Felix Bloch at Stanford and Edward Purcell at Harvard. So separate sides of the country, but they demonstrated in 1946, and they had a very quick turnaround. In 1952, they got the Nobel Prize in physics. So just 6 years later. And that's because after it was experimentally demonstrated, it quickly became commercialized. I think only about 4 or 5 years after that, then there were instruments available for many different institutions to use, and people were using this as a characterization tool. And why it's so powerful is you can get atomic level information about the surroundings of a molecule, or of nuclei or electrons, atomic level information. So the key thing is that the molecular environment will change the radio frequency bands absorbed. So this magnetic field, so this is what a typical, this is a protein NMR spectrum. So if you've seen NMR spectra for small molecules, they look much cleaner than this. You can think of the complexity of a protein, that you get these large absorption bands and peaks here. But even looking at like the number of peaks, we'll talk about this, will tell you about the atomic level structure within that molecule. So this fine level of detail is why it's so powerful. Since I keep mentioning the magnetic field, these are going to be pretty powerful and on the range of several Tesla. With these complex spectra over here, we'll get into some more details in the next lecture, that there's different types of NMR. And levels of complexity. So this is a 1D NMR of protons, or just hydrogen atoms. But you can have, like I mentioned, you can do Fourier transforms of this. You can do 2D NMR, where you're looking at different atoms within the molecule. So we'll get into some of those details. But the fact that you get this high resolution detail of the atomic structure is why it's used. So getting into the quantum description of how NMR works. First thing I want to discuss is how, I guess, and why do nuclei absorb energy in a magnetic field? So key to this is the fact that nuclei have spin. And that spin can align with or against an applied magnetic field. And we can represent this spin with a quantum number. This is usually represented as a capital I. And this is going to represent the quantized angular momentum. So if you have I equals 0, it will not work with NMR. It has no NMR properties. In that applied field, but if I does not equal 0, it will. It can align. You have an unpaired nuclear spin. So to have I not equal to 0, this is only true for atoms with odd mass. So if you have an odd number of protons, you can then have this nuclear spin occur in the magnetic field. So because of this, you can think of the periodic table, and the atoms that have an odd mass include protons or hydrogen. You can work with the carbon 13. You'll also see nitrogen at times, fluorine, and phosphorus rarely as well. So these are the typical atoms that you'll see probed in NMR. The most common I would say is proton and carbon, where carbon 13, remember, is the isotope of carbon, and it has a natural abundance of, let's see here, about 1% isotope. And also nitrogen 15 is an isotope as well, and it has a very low natural abundance of 0.37%. So with this, you'll have lower concentrations of the NMR active atoms, but you can also make your sample in isotopically pure reactants. So certain molecules will only have a carbon 13 or nitrogen in high concentrations. So that's something special with these isotope versions of these atoms. So then, based on this quantum number, you can then use some equations that then, with all of these atoms here that we're interested in, these quantum numbers will either have a value of positive 1/2 or negative 1/2 for all these guys. So with other atoms, they can also have 3/2, 5/2, and the like. But what we're concerned about with NMR spectroscopy is you're going to have quantum numbers of just positive 1/2 or negative 1/2. So aligned with the field or against the field. So using this quantum number, we can then get the potential energy of a nucleus in a given quantum state. Well, this is the quantum number that we're using here. So that equation is going to be, your potential energy is going to be negative gamma h, where I'll define gamma in a second, over 2 pi times your quantum number and your applied magnetic field, V naught. So gamma here is going to be the magnetogyric ratio. And this is going to be a value, it's going to be a set value for the atom that you're studying. And this is related to the magnetic moment over the angular momentum of the nuclei. So this is the magnetic moment. And this P is the angular momentum. And this has units of radians per Gauss second. Okay, and then this is going to be the B naught is the magnetic field strength. This is typically reported in Teslas or Gausses, or Gauss, where, as a reminder, 1 Tesla is going to be 10 to the 4th Gauss for your units. And then your MI here is going to be your 1/2 or -1/2 as well. So then in NMR, we're going to use this equation to understand what energies of electromagnetic radiation are absorbed. So we're going to use proton NMR as our example here to understand what frequencies are absorbed. And we're going to say that's going to have either MI of 1/2 or -1/2. And a Jablonski type diagram representation and energy level diagram, we have energy, and we're going to have our ground state of -1/2, our lower energy state, not ground state, and +1/2. And we want to understand if we send in a photon, what will be absorbed and promote the energy of this nuclear, switch the nuclear spin to the higher level energy. We want to understand what frequency is absorbed here. So if we're working with proton NMR, the that's a weird word. Magnetogyric ratio value is going to be 2.67 times 10 to the 8th radians per Tesla second. And we're going to be measuring this in an NMR that has an applied field of 3 Teslas. So if we want to understand the energy difference between being at a quantum state of -1/2 to +1/2, we can then plug it in that equation on the slide before and take the difference. So this is going to be our energy difference that we're looking at is going to be everything, all the constants that we have here. Of our final state minus our initial state, quantum state here. So this is going to be positive. Sorry, switch these guys. This is going to be positive, this is going to be negative. So we're going to have -1/2 minus +1/2 here.
Yeah, Professor Kifley.
Yeah.
I'm just a little confused because I thought the +1/2 corresponded to being aligned with the magnetic field. So in this case, would it be going from being aligned with the magnetic field to being aligned against the magnetic field?
Yeah, give me 1 second. Yeah, so yeah, I switched that. The positive sign is going to be your lower state and the negative is going to be the higher state. So the negative is against the magnetic field and the positive is with the magnetic field. Does that clarify it?
I mean, I thought like when you like perform NMR, like the idea is that like you place a atom in like a magnetic field, and then like there's like of course like a lag time to like until it becomes aligned with the magnetic field, right? So I'm kind of confused why we're going from with to against, if that makes sense. I mean, I'm just me understanding like NMR just because I like only like took like a single class.
Yeah, so I'm saying, so this is going to be not a pulse right here for this problem. We're not going to be working with like a pulsed magnetic field. It's just going to be a steady state magnetic field.
Okay.
And does that help?
I think so. Like, I'm not sure. I'll like take a look. I'll take a look at it like myself.
Yeah, let's, and if you still confusing after we get through, let's say slide 7 is when we're going to finish up the quantum description. So I'll pause there, and if you it's still confusing, or if you still have a question, please ask them. Okay. Okay. So getting back to this calculation of the energy difference, if we do the math over here of our quantum states, this is just going to give us -1. So the value, if we take -1 times the negative sign here, that's just going to give us positive gamma h over 2 pi times our magnetic field. And if we plug in all the numbers for this, what our energy difference is going to be 8.46 times 10 to the -26 joules. And then if we use Planck's relationship of E equals h nu, we can then plug in our energy value here. And with Planck's constant, then we can get our frequency that would cause this absorption. The frequency that would be absorbed is going to be 1.28 times 10 to the 8 hertz, or 128 megahertz. So you have to be using an NMR that can work in this range. This is our radio frequency, and this frequency that's absorbed is also called the Larmor frequency. Missing an M, LARMOR frequency. And that's the frequency that corresponds to what will be absorbed based on the splitting of the spin states. So this is with an NMR that we're using that has an applied field of 3 Tesla. What if we use Earth's magnetic field? Instead. So Earth's magnetic field is around 50 microtesla, much lower than 3 Tesla. And if we plug those values in here, so this would be substituted in for B, this value is going to scale much smaller, and the corresponding frequency is going to be the energy is going to be 1.4 times 10 to the -30th joules, or the frequency would be 2.13 kilohertz. So you can see that as the applied field changes, the energy level differences, this is 4 orders of magnitude less than up here. So that's why many NMRs, the strength of your NMR is it's going to be better if you have a higher magnetic field. So we can draw this as an energy diagram versus your applied field. And if we start with no applied field, there's going to be no separation in the energy of these 2 spins. And as you apply, you're going to have a linear difference in the energy levels here. So this is what we just calculated, this energy difference, which is the difference of the -1/2 state minus the energy of the +1/2 state. And this splitting of the energy levels of nuclear spins versus the magnetic field, this is called the Zeeman effect, or Zeeman splitting. So when you hear anything with Zeeman, you can think of this magnetic field. That terminology comes up quite a bit. So to give you an idea, we looked at Earth's magnetic field and also this model NMR of 3 Tesla. There's different scales of the magnetic fields that we just said. So let's take a certain source versus the scale in Tesla. We said 5 times 10 to the negative 5th here. If you look at the magnet that's in a refrigerator, your refrigerator magnets. So refrigerator magnets, hanging things up, 0.1 Tesla or so. And then we'll get into and discuss applications of NMR to more medical applications, but with MRI, the scale is going to be 1 to 4 Tesla or so. A low end NMR is going to be on this scale as well, maybe let's say like 1.5. The strongest permanent magnet that naturally occurs is 2.4, and a high end, the highest end NMR, we're going to get much more extreme, is 28 Tesla. So you'll see over time, when I was looking at my notes from when I was an undergraduate student back in, I guess that was from 2008, this was 21 Tesla. And as NMR from Brooker, from other vendors, they develop better and better NMRs and can afford the magnets. This 28 Tesla NMR, I think, came on the market around 2015 or 2016. And these things are tens of millions of dollars. So usually university has to write like a big grant to get this equipment. So one of these was just installed at Ohio State, I think in 2018 or so. And there's probably a dozen or so around the country. There's also specialized magnetic fields and very high-end NMRs that are not commercial, but custom built. And the magnetic field there is 45 Tesla. And this is at Florida State University, and they have like a whole magnet facility there. And it's kind of crazy if you go to their website and they describe this, just having the cooling, you have to have liquid nitrogen, liquid helium, and it takes $1,500 an hour just to run the instrument. And I would say this scale of NMR isn't used for biophysics applications. You'll see this more used for condensed matter and solid state physics work. And then you can even get higher fields if you pulse the magnetic field, and you obviously want it to be non-destructive. And the highest pulse that's been achieved is 100 Tesla. They broke this limit, I think, back in 2016 as well. And this is only like a millisecond long pulse. And again, that's more for condensed matter physics and solid state applications of study. And this was at Los Alamos National Lab. So you see there's a lot of resources you need to achieve that. So this, since we haven't been talking about magnetic fields, that's why I wanted to talk about these scales. And what you'll see, we're going to be working in or discussing in NMR is in this regime. And later in the semester, I guess at the start of November, we'll also go over some of the instruments that are in the chemistry shared facilities, and there are NMRs there. So that's where we can get into the details of what's available here at Case Western. So with these different applied fields, we talked about the energy difference. If we go back to our example case, the energy difference for our proton in a 3 Tesla field, I'm just going to write this out again, 8.46 times 10 to the negative 26 joules. And I want to point out when we're drawing these Zeeman diagrams or any energy diagrams, the question and related to the quantum description of NMR is how many nuclei are in the excited state versus that ground state. And we can use a Boltzmann description to get this number. So we're calling Boltzmann distribution. We have a Boltzmann constant, our temperature, we're going to use room temperature, and our energy difference here, where NJ is going to be the number of excited state nuclei. And Ni is going to be the ground state. And if we plug in this number here, and then use for our temperature, we're going to use 298 Kelvin, and the Boltzmann constant here, 1.38 times 10 to the negative 23rd joules Kelvin. What this ratio ends up being, if you do the math, is going to be a very small difference, 0.999949794. So, and if we invert this, and if we say that, and if we fix NJ to 1,000,000 nuclei, Ni is going to be 1.00002 times 10 to the 6. So you can see it's a very small difference in the number of excited nuclei and ground nuclei. So this is why using stronger magnetic fields will change these relative populations. And if you use a stronger magnetic field, you're going to have a larger signal intensity, and you're going to have better resolution as well. So the signal intensity, that's going to be like how strong the peak is, and your resolution is going to be like the separation of those peaks. So I'm drawing these arrows like the y-axis and the x-axis here. And just pointing out, you could have done a calculation like this with the Boltzmann distribution for energy differences in visible light spectroscopy, and these numbers would be even smaller than with that discussion. So I'll stop here right now. If anyone has, well, I guess stop here with discussing the quantum stuff, and then we'll move to the classical description. But do people have any questions about this? Was it cleared up, Todd, a bit?
Yeah, it was just like a really small mistake. I just didn't realize a photon came along to like give the particle energy to go from the lower to higher energy state. Like, it was just like a mistake on my part.
Yeah, and I'll say, like, I find NMR, like, thinking through of all the processes, because you have the magnetic field first splitting these energy levels and then a photon absorption, since there's two things going on here compared to the spectroscopy we've been discussing before. That sorting those things out makes NMR, I guess, one step more complicated, I think. Any other questions from people? Okay. So yeah, I think the important things here is realizing this equation And then that can also be related to the total actual numbers of the spins with the Boltzmann equation will come into play. We can also get these same type of equations of getting what the frequency is that will be absorbed from a classical treatment of NMR instead. And instead of thinking of individual nuclei, what their spin are, you treat these as a whole, and you can call this a spin packet in the classical treatment. So a spin packet would be group all the nuclear spins together. And then you can treat it as a net vector. So you can see this kind of illustrated over here, where you can see that there's a spin downwards and upwards. And they have some angular momentum. That's what this circle here is representing. How we discussed P, some angular momentum of that spin. We can then group all of the spins together in this very simplified cartoon. You can see there's 3 arrows pointing down, only 2 arrows pointing up. So then you can say the net vector overall, if you sum all the spins together, you're going to have your spin packet of what the ensemble classical magnetic spin is. So if you take the spin packet at equilibrium, the net magnetization should align with the external field. And then you expose to your NMR frequency. NMR frequency. So remember that's the frequency of gamma B over 2 pi. This is the same equation that we had from the quantum treatment, and that corresponds to the delta E of the spin states. So you would sweep the classical treatment, you would sweep through these different frequencies, and you would find where the peaks are located at would correspond to this delta E. And this is identical to the quantum mechanical description. So we discussed like at equilibrium with the applied field, you see this alignment, but after you turn the field off, your spins relax down. And the way they do that, and when we get into the instrumentation, we'll talk about monitoring that relaxation, is there's 2 processes or times for that relaxation. And this is important to know, these 2 characteristic times, and these times give you information about the environment as well. So with time-dependent NMR, characterizing what these values are and what they correspond to is a key thing. So one of them is a spin relaxation, spin lattice relaxation. And this is the energy of the nucleus is given to the surroundings. So this is called, when people describe the times, they typically call it T1, and it's called the longitudinal relaxation. And this is the average lifetime of the nuclei in the excited state. So this is our T1. Another type of relaxation is grouped together, actually, and can account for, this is called T2 creatively. And this includes spin-spin relaxation. And this is energy of the nucleus is given to neighboring nuclei. So you can think, if a nuclei is in a given state and its neighbors are in the ground state, and then pass that energy over, and you can end up with dissipation of that energy. So this is called transverse. T2 is typically called the transverse relaxation time. And it includes the spin-spin relaxation, but it also includes other relaxations that we're not going to describe in detail, but you might hear terminology like J coupling, and that has to do with energy dissipation between covalent bonds of atoms, or you'll see quadrupole coupling. And this has to do with like electrons and energy dissipation based on the electric field of the electrons that are around. So in measurements where they're looking at T1 and T2, T1, it's worth noting, is always greater than T2. It's always going to be a faster process than these group spin-spin relaxations and other types of coupling. That the energy dissipation to just the surrounding environment is always going to be the fastest process that takes place. So that's the relaxation that you can observe in pulsed NMR. But one of the powerful, and that can be related to the environment, but also chemical shifts and what you see in the spectrum at steady state, not necessarily over time, is why NMR is a powerful technique to look at biophysical structure. So it can look, first we'll talk about how the environmental effects of the electrons surrounding the nuclei. And how this is observed, it has to do with the chemical shift. So the chemical shift has to do on your axes in your NMR spectrum, where are the peaks on this x-axis? And this is related to the electron distribution because electrons generate their own magnetic field since they're moving in the sample. And it usually opposes the magnetic field. So we can say what the shift in the magnetic field is, has to do with that electron shielding. It's going to be the applied magnetic field minus some effect of the electrons, which we're calling sigma times that applied field, which we can then simplify this equation to pulling out the applied magnetic field out front, 1 minus sigma. So this B naught here is the resulting magnetic field. And this is actually what determines the behavior of the nuclei. Which this B applied is going to be like the applied field by the NMR. And our sigma here is going to be called the screening constant. And that's based on the electron density. What's the effect of the electrons around the nucleus? So you can then take this equation and we can plug it into the equations that we have on slide 5 that are about the energy difference and our frequency that's absorbed. And what we would get for the frequency that's absorbed would be gamma over 2 pi times B naught times 1 minus sigma. So we substitute our actual observed magnetic field. I think this should be applied here. I'll double check. In the notes I have a B naught, but I think that should be applied there. I'll double check. And if it's wrong in the notes, I'll send an update. But this is the frequency that you then observe in your NMR. An important thing with the frequency, you can see that in typical NMR, it's reported as this lowercase delta as opposed to the actual frequency in hertz. And you typically don't see NMR with the hertz, with frequency as the x-axis label. And that's because the NMR instrument itself can have a lot of variation. And you want to be able to report your results in a way that isn't dependent on the NMR instrument that you're using. Because the NMR, if you take a measurement on one NMR and then you go, someone wants to repeat your work and do a measurement on a different NMR, you want to be able to compare those results directly. So what is typically used for the chemical shift is it's plotted compared to an internal standard. And I don't know if you guys remember from the second lecture, and Rose asked for an example, and I gave an example from NMR spectroscopy. So the internal standard that it's plotted relative to is typically you dope your sample with something called TMS if you're using an organic solvent. So that's trimethoxysilane. So there's a lot of hydrogen protons that are present there that are all equivalent, so it gives a nice large signal. That's what's shown on this example NMR here, but this is a biophysics class, so typically you're not doing your measurements in an organic solvent. So if you're doing an aqueous solution, you use something called DSS. Let me look at the chemical name for that guy. It's somewhere. It's a type of salt. It has sodium in it. 2,2-dimethyl 2-silopentane 5-sulfonic acid. So there's not salt in it. But this is your aqueous standard. And the key thing with these guys, there's a lot of protons if you're doing, these are the standards for proton NMR. So there's a lot of protons there, so they'll have a nice signal. And then what you look at is the difference in your signal compared to that peak location. So your internal standard is always going to be at 0 ppm for your chemical shift. This is always reported as parts per million. Since the shifts are small, and how you calculate the chemical shift Delta is the absolute value of the frequency of your internal standard minus the frequency of your analyte, what you're interested in, all divided by the frequency of the internal standard times 10 to the 6. So you can see this parts per million comes from this factor over here. So the chemical shift has to do with the electron cloud, the electrons that are screening your nuclei. But you can also have effects of neighboring nuclei as well. And how this shows up in NMR is how many peaks. So doing a very easy example, if we have a methyl, I guess I just rewrote that. You have a methyl group here. You have 3 protons that are identical to one another. How their spins can align, let's say this is our applied magnetic field. The spins of these 3 separate protons, they can all be aligned. The quantum state can all be aligned against the field. You can have 2 aligned against, 1 with, in these 3 different conformations, 2 aligned with the field and 1 against, or all with. So what you see is, you see this show up in the number of peaks and also their height as well. So with this state, a very simple of the quantum states of these methyl protons, what this shows up as is this grouped peak over here, where you see 4 peaks total, 2 small ones on the edge, 2 larger ones in the center. And if you integrate the areas of those, what you're going to see is an actual ratio of 1 to 3 to 3 to 1 with those. Similarly, we can think of this group, a methylene group with 2 protons, and you'll have more simple alignments, or you'll have 3 possible conformations, 3 peak locations at a 1 to 2 to 1 ratio, which is this guy shown here in this diagram. So peak location in your spectrum is going to tell you about the electrons. Number of peaks and peak height will tell you about the number and the nuclei effects on each other. So any questions about that, about the classical description and also like reading or interpreting an NMR spectrum?
I did. So I was wondering, like, if I understand this correctly, the way we categorize like different like materials or something, like, or like just like our samples, is by looking at how long it takes for nuclei to return to an equilibrium state after the magnetic field is turned off.
Mm-hmm.
Okay, so like
So that's one way, and then also looking at this, I guess these spectra would be after doing post-processing and getting like a steady state type measurement.
Oh, okay, so I misunderstood. So like in the beginning, I had the assumption that the way we did it was by looking at how long it took for the atoms to align with the magnetic field, but just like the actual way is by looking at how long it takes for to reach an equilibrium state after the magnetic field is turned off.
Yeah, so at the start when we're talking about the energy difference, that's going to be looking at the absorption of radio frequency, the radio regime of light after it's in the magnetic field and it's at equilibrium. So that's what these, I'm pointing at my screen, you guys can see that. What these spectra would be the equivalent of. The relaxation times is looking at this versus time. I don't have example plots here, but in the next lecture, that's the problem. This is more focused on the theory behind it. The next lecture, we'll get into example spectra, example data, and hopefully that will be more clear that looking at the relaxation times, these type of spectra that I'm showing here don't have any information about relaxation after the magnetic field is turned off. That would be a different, more time-dependent measurement. But realizing that these nuclei can interact with the environment, interact with neighboring nuclei or electrons, shows up both with that time-dependent relaxation and then also the steady state spectrum as well.
I also had a follow-up question, but like I'm like pretty tired right now, so I'm not really like, I don't think I'm following everything. So if you want me to save the question for like the end, that's fine.
There's only one more slide, so you can ask it now. That's fine.
Okay, cool. So when you talk about like the when we look at relaxation time, and we have the nuclei return to the equilibrium state.
Mm-hmm.
Before you define like at equilibrium and that magnetization of the samples align with an external field, so it's confused like exactly what equilibrium state they would return to, if that makes sense, or like after the magnetic field is turned off.
So if the magnetic field is being turned off, it's going to there's no field to align to. So then they're gonna, if we go back to the Zeeman diagram, after it's turned off, they're gonna be returning to a state where the spins don't have an energy splitting here. So there's no light and absorb over there.
Oh, okay, thank you.
Yeah. Cool. Any other questions? Okay. Last slide is about shifting gears to EPR, electron paramagnetic resonance spectroscopy. It's also called electron spin resonance spectroscopy. So ESR, it'll also be referred to. And it's the same thing as NMR, except it's with unpaired electrons. If you have an unpaired electron field, magnetic field, it can be aligned with or against that field. The thing with EPR is that having unpaired electrons is rare. Another name for an unpaired electron is an radical, and radicals react quickly. So you typically have to have you have to do some labeling. Some form of a stable radical. So I have an example here of, you can see there's a radical on this group, on this oxygen right here, an unpaired electron, and you can have specific chemistry that will react with the thiol. So when we talked about bioconjugation and putting labels on, fluorescent labels on molecules, similar concepts can be used in EPR, except you're using, instead of a fluorophore or a diene over here, you're having a radical label instead. So this isn't used as frequently because all biomolecules will have protons present and carbon present and nitrogen present. So it's very easy to have these naturally, you won't have to label your molecule in NMR, but you do have to label your molecule in EPR. Another difference from NMR is that electron spin is in a different regime. Of the electromagnetic spectrum. So this is actually in the microwave regime. So you're using longer wavelengths, so then you have to, or using shorter wavelengths, excuse me. So you have to have different instrumentation. Than NMR. So because of this labeling, there might be I think there might be one EPR on campus, I think in the biophysics department, but we probably have like dozens, if not, maybe, I'm gonna guess, on campus. I'll have to do the numbers, but there's definitely multiple, more than enough NMRs, but that's a more general technique compared to EPR is viewed as somewhat specialized. But we'll talk about the difference in the instrumentation in the next lecture. You can find in chapter 5, this section goes over NMR. Chapter 19 of the instrumental book is all about NMR. And I just also want to emphasize that we're going over NMR in 2 classes, but you can spend an entire semester or multiple semesters focusing on this. So if you want to know more and get into all the details, you can sign up for Professor Brown's class, and Professor Martin's, I think, teaches this as well. And then also in chemistry, if you want to be looking at this for small molecules, there's a whole course that will go over like interpreting those spectra and the like. So any questions? Let's see if there's something in the chat. Okay. Daniel says that there's 8 to 9 NMRs, he thinks. So yeah, when we get, and Colin said that he took the chemistry class and was very detailed. So yeah, you guys probably know more about NMR than me if you guys took those classes. And who teaches 325, 425?
That's Dr. Zagorski.
So yeah, definitely in the organic synthesis regime, people use NMR a lot. It's very key.